So we started out by saying we were going to generalize what we had for the in the context of periodic signals in discrete time. We had x of n periodic with fundamental period n and the associated fundamental frequency. I'll just write frequency, 2 pi divided by n. And what we know that we could do for such signals is think about them in terms of their a frequency domain representation, where we took a linear combination of these harmonically related complex exponential signals. So these are functions of time n. The frequencies that they're corresponding to are k times that fundamental frequency, k times 2 pi over n. And we saw that we could take, these guys are periodic, a sub k plus n is equal to a sub k. That's something we used on the midterm. And so we could take any sequence of n of those in a row to build up that signal. And how did we get those a sub k's? Well, we got them through the analysis equation, which sort of resembled the analysis equation that we had for the Fourier series in continuous time. We take our samples of our signal, x of n, and multiply by e to the minus jk 2 pi over capital N, so e to the minus jk omega naught n. This is when we're trying to find a sub k, the kth coefficient, so there's where that index of the coefficient comes in, and we sum over one period of the signal. And as I say, if you kind of plug in k plus capital N into this thing, you'll see that when you evaluate this, you get the same thing as a sub k, because the k plus capital N, when you add capital N, you just are adding 2 pi to that angle. And when you add 2 pi to the angle, you get the same thing. So that's the Fourier series. And then we said we were going to soup that up for aperiodic signals. And we kind of developed this set of equations by mimicking what we did in continuous time. We started out saying, let's assume that the signal is finite duration and then just make it periodic. And then apply this stuff to that periodic signal and then just push the period out to infinity. So we get all of the copies pushed off to infinity and we're left just with that finite duration signal. And we found that we could express the signal in terms of an integral equation. So when we go to the aperiodic setting, we get something that involves not a summation as in the Fourier series, but now it involves an integral. And the thing that represents the transform, it represents kind of the content of that signal at each frequency omega, is this x of e to the j omega. So it's similar in form to this. Here we were taking the content at k omega naught and using it as the weighting factor for e to the jk omega naught n. Here we're taking the content at frequency omega and using it as the weight, so to speak, the coefficient in front of e to the j omega n. And then we just integrate over the omegas. But this thing turns out to be periodic, just like this thing is periodic. The a sub k's were periodic. This turns out to be periodic. And its definition, which came out of that analysis using the Fourier series applied to that periodic replica of the finite duration signal, turns out to be something that actually looks pretty familiar. We got it by taking the samples of our signal, x of n, and then using them to weight e to the minus j omega n. So when x of n is equal to the impulse response of the LTI system, call it S, then the resulting discrete time Fourier transform is nothing other than the thing that we had said was the frequency response of our system. And if you remember, this was just a special case. This was equal to h of z. Remember, h of z, the system function, was the sum of h of n, z to the minus n. And all we did here was we just said, let's set z equal to e to the j omega. So we can evaluate this, right? This is the eigenfunction scalar, the eigenvalue associated with z to the n for that LTI system. This is the eigenvalue associated with e to the j omega n. And so we just substitute z equals e to the j omega. So we've actually seen it before. Now there are some conditions having to do with the existence of this. In order for this to, we require some conditions on x of n for this thing, for this infinite summation to converge. So the one that we typically choose to invoke is very much kind of like the analogous thing that we had for the stability of a system, which was we want the sum of x of n to be bounded. So we want x of n to be absolutely summable. And over here, that condition, when we put that in, now I haven't proved that we require this, but it's kind of this, the theory behind it is similar to sort of the convergence issues we had with the Fourier transform. And so this condition, actually, when we put it over here, we actually want to insist, just like in continuous time, we want the system to be stable. Okay? So just as in continuous time, we saw that we wanted to have something like the Dirichlet conditions hold, and when we translated that into the LTI system context, that meant that we wanted our system to be a stable LTI system. We wanted that, in that case, it was absolute integrability. Now, if you remember what we did with Fourier transform in continuous time is we started out with Fourier series. We then moved to Fourier transform, and then we said we'd like to be able to kind of use these things together, these types of signals together, just like we did in modulation and in sampling. So we need one more ingredient. We need the notion of the discrete time Fourier transform for periodic signals. And we basically play the same game that we played in continuous time. We look, if we try to evaluate this directly for a periodic signal, we end up running into problems, just like we ran into problems when we tried to figure out the continuous time Fourier transform of e to the j omega t. We plugged that into the analysis equation for the Fourier transform, and we got this thing that sort of didn't make sense. We were trying to evaluate a periodic signal at infinity and minus infinity. Well, if it's periodic, it doesn't have a value at plus and minus infinity because it's always going up and down. Same kind of problem arises here. So we basically fake it. We kind of say, look, what do we think it should look like? And then let's plug that thing that we think it should look like into this equation and make sure that when we try to synthesize our periodic signal, we get this back again. And so what we get in the case of the periodic signals, well, we already know something about the structure of our periodic signal. So we want the synthesis equation to be valid. So what I need to define is what I want to have for my Fourier transform. So we know it's periodic, so we actually know how to write it already. We write it like that. The sum of a sub k e to the jk 2 pi over n times n. So we have these Fourier series coefficients, and we figure that the Fourier transform should somehow be related to these. Now, we would expect that just like in continuous time, remember this is a continuous function of frequency, if this thing is concentrated at harmonics of 2 pi over n, we sort of expect the Fourier transform to have impulses at multiples of the harmonic frequency. So if we're given this, what we are going to say as the form of the Fourier transform to make that synthesis equation work is we're going to again use a sub k as the nominal weight associated with an impulse, and the impulse should be located at, well, at these harmonics. So it should be at k times 2 pi over n. Now, if we try to plug this into the, actually before I get to that, let me point out now, you may say, well, what should this set of impulses look like? Should it be a finite set of impulses? Because when we write the synthesis equation over there, we're just adding up a finite number of harmonics. But remember, this x of e to the j omega is periodic with period 2 pi. So a key property of this, just as we had the periodicity of the Fourier series, we have a periodicity that this is periodic with period 2 pi. So we know that this x of e to the j omega has to be periodic. So this thing can't just stop after a finite number of impulses. It has to repeat. So what we do is we just basically let this run over all possible ones. So just to give you an example, suppose we took x of n equals, I'm going to do it actually for a general. This was for kind of a truly periodic signal. But we could start out and just say, let's look at x of n equals e to the j omega naught n. So that might not actually be periodic unless omega naught is a rational multiple of 2 pi. But just as in continuous time, we can kind of look at this thing and we can say, well, what should we, what would make, what choice of x of e to the j omega would make that synthesis equation hold? So we would think that this thing should look like an impulse at, well, at this frequency. So it's going to be at omega minus omega naught. That would be sort of the pure impulse at the frequency where we would expect to see an impulse. But we know this thing has to be periodic. So I can't get away with just doing that. I have to repeat it. I have to repeat it every 2 pi. So this has to repeat every 2 pi. And so what I have to put in here is omega minus omega naught plus 2 pi k. And I have to sum over all possible multiples of 2 pi. But now if I plug this into the synthesis equation, I'm going to integrate over one period. So why don't I pick the period that just includes this guy. When I do that, what I'm going to get is the integral of this. Well, that's going to turn out to be 1, right? Because we're just integrating an impulse. But I have this 1 over 2 pi in the synthesis equation. So if I'm going to make that work, I've got to multiply this by 2 pi. And basically, we're using this result in this expression. And we just, because of this fact that we have to have all these copies every 2 pi, we end up with an expression that looks like this. So it's going to be, you can imagine the interval of 2 pi, 0 to 2 pi, broken up into n harmonics. And then each of those harmonics has to get repeated. You know, we have to, whatever that contribution is there for each one of those has to get repeated every 2 pi. And so it actually covers all of the multiples of 2 pi over n. And that's why we end up with this expression. Okay? So you can use this to figure out what the discrete time Fourier transform of, let's say, a cosine looks like. Well, the cosine is just going to be e to the j omega naught n plus e to the minus j omega naught n divided by 2. So you're just going to basically take this guy. You'll have these at plus omega naught and integer multiples of 2 pi in both directions. And then you're going to have one at negative omega naught plus all of its repeats every integer multiple of 2 pi. So it's a real, looks like a big mess, but if you just look at one period of it, it's going to look like what you'd expect. You're going to see something at minus omega naught and plus omega naught. But then you have to put in all their repeats in both directions. Okay, so that's kind of the whole story now on the discrete time Fourier transform. The other thing that we always talk about with these transforms is we talk about their properties. And there are, again, just as in continuous time, some key properties that matter to us, particularly when we're analyzing difference equations. And as I mentioned last time, yeah, so I should maybe just say over here, DTFT transform pairs, those are in table 5.2, and the properties are in 5.1. So there's a whole slew of them. We're going to be interested primarily in the ones that, as I say, matter when we're looking at difference equations. So there's the periodicity property, which is kind of unique to the discrete time setting. Then linearity, time shift, phase shift, conjugation, time reversal. They look very much like what we saw in continuous time, except of having x of j omega, we've got x of e to the j omega or e to the minus j omega, depending on what the property is. And then that includes Parseval. And then the two that really we use a lot, along with the time shift, are convolution and multiplication. So particularly convolution, because that's the one that crops up in the context of LTI systems. So what we would know from this is that if we have an input to an LTI system, x of n, if its impulse response is h of n, then the resulting output is just y of n equals x of n convolved with h of n. And what's the Fourier transform of the output? It's just the product of the transform of the signal with the frequency response. So again, convolution in time domain becomes multiplication in frequency domain. And that's really the key one that we're interested in.